In chapter 4, we're going to talk about probability and probability distribution. So to start off, we're going to talk about some basic probability rules and what probability is. So probability has to do with randomness. So rock, paper, scissors, coin tosses, lottery and casinos, games involving dice spinners or cards, even inherited traits such as gender, hair and eye color, blood type, dimples, all are determined by the chance involved in which genes get passed along. So all of these represent chance behavior. And we can work and understand with this because we know all of the outcomes. And all of these outcomes are governed by chance, but in many repetitions, a pattern emerges. So in the short term, there may not seem to be a pattern, but in the long term, we can see one. So we use mathematics to understand the patterns of chance behavior, which is how we get to probability. So when we define probability, it is the probability of any outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. So a probability of 0 can happen. It would just mean that the event will never occur. And then a probability of 1 means that it will always happen. So the idea of probability seems very straightforward. It answers the question, what would happen if I did this many times? So randomness is only predictable in the long run. And unfortunately, our intuition about randomness tries to tell us that random phenomena should also be predictable in the short run, which we'll talk about more in a little bit. So there's two types of probability that describe chance. The first one is empirical probability. And it's based on actual observation. So if you flip a coin 500 times and you get heads 489 times, the empirical probability is 489 out of 500. What most people are familiar with is the next type, which is theoretical probability. So it takes empirical probability based on an infinite number of trials. So for example, we'd expect that out of an infinite number of flips, half of them should land on heads. So theoretical probability of a coin landing on heads is 0.5. So empirical is what happens if you actually do it. Theoretical is what you expect to happen. So with our idea, the intuition of randomness being predictable in the short run, we get something called the law of averages. So it's very common for people to think that you can make predictions about future outcomes based on past behavior, which is unfortunately not something you can actually do. So, for example, women have a 50% chance of having a boy with each pregnancy. So the gender of any previous children does not matter. So you'll get a lot of the times that, a woman's had 4 children, they're all girls. So people will say, well, she's due a boy. But the probability each time she gets pregnant of having a girl or a boy stays 50%. It's also very a common thing to hear in baseball. So you have batting averages, which is how often a player gets on base. And if a batter hasn't been on base or gotten a hit, a lot of people will say, well, he's due to get a hit or on base. And so that's the myth of the law of average. They use past behavior to kind of predict something that is going to happen in the future, which we cannot do. So a couple basic things about probability. So it is always a number between 0 and 1. It is a long run proportion of repetitions in which the event occurs. All possible outcomes together have to have probabilities that add up to 1. So based on however many outcomes you have, all of their probabilities together have to add to 1. We can also look at the probability that an event does not occur. So that is, if we're using probability notation, 1 minus the probability the event does occur. So if you think of it as there's only ever 2 outcomes, something does or doesn't happen, then they have to add to 1. So we refer to something as not happening as the complement, and we always denote it with a C as kind of like an exponent. So that would say the probability of something not happening. Couple different ways you can write this probability. So we can say the probability of some event A is equal to 1 minus the probability of it not happening. We also know that because these are only 2 outcomes, the probability of A and not A together have to equal 1. Or thirdly, we can say that the probability of not A is 1 minus the probability that it does happen. So that would be the probability of A. So all 3 of these are basically the same thing, just rewriting it in a different way. So let's talk about some common terms that we're going to see related to probability. So I've already kind of talked about random event. So that is an activity or with a measurable result. So for example, flipping a coin, or rolling a die. An outcome is the result of one trial of one random event. So if, example, I flip a coin and I get heads, the outcome is heads. Or if I roll a die and I get a 3, the outcome is 3 because that happened in one thing. An event is a set of related outcomes. And then lastly, we have our sample space. And a sample space is a set of all possible outcomes. And we do denote a sample space as S equals, and then we list that sample space inside a set of curly brackets. So if I'm going to go back to flipping a coin or rolling a die, I can list the sample space of flipping a coin as heads and then tails. And then for flipping a coin, it's the numbers 1 through 6. So we always just list them inside the brackets separated by commas. So when it comes to calculating probability, it is the number of outcomes in the event divided by the number of outcomes in the sample space. So if we have some letter E that represents our event, so the probability of our event E equals the number of outcomes in the event divided by the sample space. Now, with this formula, all of the outcomes in the sample space have to be equally likely. So if you're dealing with a weighted coin or a weighted die where some outcomes are more likely than others, then this formula doesn't work. But we're going to be dealing with probability where outcomes are equally likely. So let's look at an example. We have a bag that contains 10 marbles, 2 black, 3 blue, 1 red, and 4 white. So we want to find the probability of pulling out a black marble. So my probability has to equal my total number of black, 2, over my total sample space, which is 10. And when you have smaller fractions like this, we do like to simplify them. So 2/10 simplifies to 1/5. And I can leave it as 1/5, or you can write it as a decimal. So 1/5 is 0.20. Okay. For my second example, we want to know the probability of pulling out a red marble. So we have a total of 1 red marble over my 10, which does not simplify, so the answer is 1/10 or 0.10. Okay. A very common example that we're going to deal with are dice, either single dice or rolling 2 dice. So we have that 2 dice are rolled and the sum of the pips, which is what those dots are called, is noted. And we want to know the probability that a sum of 9 is rolled. So the first thing is to figure out how many outcomes are there when you roll 2 dice, and then also how many ways are there to get 9. So we're gonna first create a table where we can look at all of the possible outcomes of rolling 2 dice. So you have the numbers 1 through 6. That can happen for both of the die. Okay. So if you roll 2 1s, then you would fill in this table with the sum. So if I roll 2 1s, I get a sum of 2. If I roll a 1 and a 2, then I get a 3, 4, 5, 6, 7. And then 3, 4, 5, 6, 7, 8. So I continue filling out my table. So something very common we're going to deal with is knowing that there are 36 outcomes when you roll 2 dice. Whether that's, getting a 1 and a 1, a 1 and a 2, so on and so forth, or looking at the sum of those 2 die. And then the next part of this is how many of those result in a sum of 9. So then I'm going through and I'm picking out how many ways can I get a 9. And there are 4 ways to get a 9. So the first die being a 3 and the second one being a 6 is considered a different outcome than the first one being a 6 and the second one being a 3. So the probability of getting a sum of 9 is going to equal 4 out of 36, which is going to simplify to 1/9. Now, I don't like to write fractions like 1/9 as decimals because they are not nice decimals. So 1 divided by 9 is actually 0.1 repeating. So if you are going to do a decimal, I just ask that you do a minimum of 3 decimal places anytime. You can go more than 3, but 3 is the smallest amount. So in our next example, we are flipping a coin 3 times. And we want to know the probability that exactly one of the flips results in heads. So similar to the last example, we kind of want to list our outcomes for when we flip 3 coins. So we could get that all 3 of the flips result in heads. We could get that only one of them results in heads. Now, whether it's the first, the second, or the third flip that results in the heads, we don't know. So each of those 3 possibilities are considered a separate outcome. So heads, tails, 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 heads, tails, or tails, tails, heads. And then we can also get 2 heads. So whether it's 2 heads in a row and then tails, or heads, tails, heads, or even tails, heads, heads. And then the last option is that none of them are. So that would be 3 tails. So if we look, there are 8 outcomes when you are flipping 3 coins. So exactly one of them being heads, there were 3 different ways for that to happen. So the probability of exactly 1 heads equals 3/8, which you can write as a decimal if you want, which is 0.375. On the reverse side of the things, we could say, what's the probability that at least 1 resulted in heads? So that means we could have 1, 2, or 3. Another way to look at this, if you think about in terms of complement, so the probability that at least 1 of them is heads is the same thing as 1 minus the probability that none of them are heads. So in that case, since there was only 1 outcome with none of them being heads, it's 1 minus 1/8, which gives us 7/8, which as a decimal is 0.875. You can also do it where you're like, all right, how many times can I get at least 1 heads, which happened 7 times, because every outcome but 3 tails resulted in at least 1 heads. So that was looking at probabilities of individual events. So now we're going to start looking at probabilities associated with 2 or more events. So if 2 events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. And we say when 2 events have no outcomes in common, they're referred to as mutually exclusive or disjoint events. So in other words, the probability of A and B, so the probability of those 2 events occurring, is 0. So it's kind of like if you flip a coin and can you get heads and tails? So heads and tails are mutually exclusive. I cannot flip a coin and get both of them at the same time. So here's a much nicer image of all of the outcomes of rolling 2 die. So the first one being the red and the second one being white. So we want to know the probability of getting a sum of 5 or 2 even numbers. So I want to go and pick out all of the different ways to get 5. So that could be 4 and 1, 3 and 2, 2 and 3, or 1 and 4. And then my 2 even numbers, 2 and 2, 4 and 2, 6 and 2. I'm going to do that in a different color. So 2 and 2, 4 and 2, 6 and 2. And then we can also do 4 and 4, 2 and 4, 6 and 4. And then 2 and 6, 4 and 6, 6 and 6. So in this case, when I was highlighting, I didn't highlight anything twice. So these are mutually exclusive events. I can't get a sum of 5 by adding 2 even numbers. So I can take the probability of a sum of 5, and I can just add the probability we get 2 even numbers. So there are 4 out of 36 outcomes that result in a sum of 5, and there are 9 outcomes that result in 2 even numbers, which gives me a total probability of 13 out of 36. Which, again, if you wanted to write as a decimal, you could. Not a nice decimal, but it's about 0.3611. So if you have 2 events that are mutually exclusive, we say that the probability of A or B is the probability of A plus the probability of B. So look at a couple more examples of this. So we have that online courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who's taking an online course for credit and record the student's age. And we have a probability model. So 57% of people, so 0.57, are 18 to 23. 0.17 are 24 to 29. 0.14 are 30 to 39. And then 0.12 are 40 or over. So the first thing is to show that this is a legitimate probability model. So there are 2 things you look for in order to show this. One is that all your probabilities are between 0 and 1, which they are. And the second one has to be that the sum of all probabilities is 1. So now I just need to verify that 0.57 plus 0.17 plus 0.14 plus 0.12 equals 1, which it does. So it is a legitimate probability model. Now we want to find the probability that the chosen student is not in the traditional college age group. So that's 18 to 23. So you can, again, go about this 2 ways. You can do 1 minus the probability that someone is 18 to 23. So that's 1 minus 0.57, which is probably the easiest way to go about this, which ends up being 0.43. Your other option is to add the other 3 categories together. So 0.17 plus 0.14 plus 0.12, which also results in 0.43. So whichever way you decide to look at it, you get 0.43. So we're going to come back to our 2 die. But now we're going to change it to the probability of rolling a sum of 6 or 2 even numbers. So my first event is my sum of 6. So you can do 5 and 1, 4 and 2, 3 and 3, 2 and 4, or 1 and 5. My second event is the 2 even numbers. So 2 and 2, 4 and 2, 6 and 2, 2 and 4, 4 and 4, 6 and 6. And then we have 2 and 6, 4 and 6, and 6 and 6. Now in this case, I highlighted 2 of the outcomes that also resulted in a sum of 6. So these are not mutually exclusive events. So when that happens, we have to account for that when we calculate our probability. So we can't just add the probability of getting a sum of 6 and 2 even numbers because there is overlap. We don't want to count something multiple times. So to take care of that, we subtract the overlap. So however many they have in common. So we do the probability that you get a sum of 6 plus the probability of the two even numbers. But then we subtract the probability of getting a sum of 6 with two even numbers. So the probability to get a sum of 6 is 5 out of 36, plus my two even numbers, which is 9 out of 36. But two of my even numbers resulted in a sum of 6. So I need to subtract my overlap of 2. So we're going to get 5 plus 9 is 14, minus 2 is 12 out of 36, which does simplify to 1/3. Which again, not a nice decimal, but it's 0.3 repeating. So there's a 1 in 3 chance if you roll 2 dice, you get either a sum of 6 or two even numbers. So we can take this and create what's called a general addition rule. So it works for any two events. We say the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Now, if A and B are mutually exclusive, then obviously the probability of A and B is 0, which is how we get the addition rule that we were dealing with. So this one you can always use, whether two events are mutually exclusive or not. So this is the general one that we always use. We'll say it's A plus B minus overlap. And then if there is no overlap, then you don't have to worry about subtracting anything. So other than dice, the other really common thing to do with probability is deck of cards. So we have all of the different outcomes for a deck of cards right here. So if you don't know, a deck of cards is made up of 4 suits. You've got clubs, spades, hearts, and diamonds. Each suit has the cards ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So there are 13 cards in each suit, 4 suits total, giving you 52 cards. So for our first probability, we want to know the probability you get a red card or a queen. So there's only 2 colors, black or red. So half of the deck is red, so that's going to be 26 out of 52. And then each of our suits has a queen, so there are 4 of them. The next big thing you have to ask yourself is, okay, am I done? Are these mutually exclusive events or not? So can you get a red queen? And the answer is yes, which means these are not mutually exclusive, which means you do need to subtract the overlap. And there are 2 red queens. So 26 plus 4 is 30, minus 2 is 28. So we have 28 out of 52. Now you don't have to simplify larger fractions like this if you don't want to. You can either just leave it as the fraction 28 over 52, or you can write it as a decimal, which is going to be 0.5385. So a little over 50% chance, which makes sense because if half of the cards are red and then you're saying or a queen, it makes sense that it would be over 50%. So the next one is drawing an ace or a king. So there are 4 aces, so 4 out of 52. There are also 4 kings, 4 out of 52. Now, if I pick a card, it cannot be both an ace and a king. So these are mutually exclusive. So I don't have to subtract any overlap. So my answer is just going to be 8 over 52. Which, if I look at as a decimal, is 0.1538. So this is actually the probability of drawing any 2 cards, ace or king, 7 or 6, queen or 4. So any 2 cards have the same probability. Okay. The next one is the probability of a queen or an even number. So we've already talked about the fact that there are 4 queens in a deck of cards. Now we want to talk about even numbers. So in the even numbers, there are 5. There's 2, 4, 6, 8, and 10. So there are 5 even numbers in each suit, of which there are 4. So that means there are 20 total even numbers. Now a queen, because it's a face card, because it has a face on it, is not even or odd, so there's no overlap here. So these are mutually exclusive events. So then my probability ends up being 24 over 52, which as a decimal is 0.4615. So that would actually be true for any face card. So that's the same probability for any face card or an ace, because an ace is not a face card either. So if I interchange queen with king, jack, or ace, and I say even number, they all have the same probability. And then the last one we want to look at is the probability of black or an odd number. So if half of the deck is red, the other half is black. So we have 26 out of 52 cards that are black. The odd numbers, ace is not an odd. Even though it is considered 1 in some card games, an ace is not odd. So the only odds are 3, 5, 7, and 9. So there are 4 odds and there's 4 suits. So that gives us 16 out of 52 odd. Now, these events are not mutually exclusive because there are odd cards that are black. Half of them are. So I actually need to subtract 8 out of 52. So we're going to do 26 plus 16, which is 42, minus 8, which is going to give us 34 over 52, which is 0.6538. Incidentally enough, that is also the probability you draw a red or odd number. So a lot of probabilities in decks of cards are going to be repetitive, just because a lot of things have the same chance of happening. Our next example is going to look at a table. So we have that students in an urban school were curious about how many children regularly eat breakfast. So they conducted a survey asking, do you eat breakfast on a regular basis? And all 595 students in the school responded to the survey. And then we have a two-way table with the results. So they looked at the students who eat breakfast and don't, and then it broke it down further by gender. So if we select a student from the school at random, we want to know the probability that the student is a female. So we only care about the female. So we look at the total amount of female students, which is 275, and then it's over the total amount of students, which is 595. Again, you can leave it as the fraction, or you can write it as a decimal. So this becomes about 0.4622. The next problem, we want to find the probability that someone eats breakfast regularly. So that's total people who eat breakfast regularly, 300, over our total number of people, 595. Obviously going to be a higher probability than the previous one because there are more people. So we're going to get 0.5042. So a little over 50% of them eat breakfast. Third problem says the probability that you're a female and eat breakfast regularly. So we're looking for the females and eat breakfast regularly. So that's 110 over our total number of students, 595. Which is going to be 0.1849. So the last thing is we're going to put this all together, and we want to know the probability you get a female or someone who eats breakfast regularly. So from a two-way table, I can't just add the totals together. I can't just do 275 over 595 plus 300. I can't just add them together. One is kind of big indicator that you're going to have to subtract the overlap is you can never get a number bigger than the denominator. And if I add these together, I do get 575 over 595. So I'm not quite over 1 yet, but it is very common for that to happen. So I do need to subtract my overlap, which is the both. So that's the 110 over 595. So if I do 575 minus 110, we end up with 465 over 595, which as a decimal is 0.7815. In our last example, we're going to look at hair color and eye color for a group of women. So we have the 4 different hair colors, black, brown, red, and blonde, and then the 4 eye colors, brown, blue, hazel, and green. So one thing we do need is the total from each row and column that we're going to be looking at, and then we do need the total number of people. So I will go ahead and give you the total. So the total in the table is 313. So the first thing we want to know is if you choose a woman randomly, the probability that they have red hair and green eyes. So we're going to go ahead and find the red hair and green eyes in the table. So that's 7. So we're going to have 7 over 313. Which is 0.0224. So very, very small chance. And now we want to find the probability that she has red hair or green eyes. So now I need the total specific of red hair. So we're going to do 16 plus 7 plus 7 plus 7. So that is 37. So we're going to have 37 over 313 plus the total for green eyes. 2 plus 14 plus 7 plus 8, which is 31. And then we do need to subtract our overlap, which is that 7 over 313. So we do 37 plus 31 minus 7, and we're going to get 61 over 313, which as a decimal is 0.1949. So almost a 20% chance. So let me know if you have any questions about probability, whether it's probability from a 2-way table, probability with cards, or probability with dice.